Welcome, ladies and gentlemen. This is our last video in our kinetics unit. It is on what is called the reaction model, and as part of that, we're also going to be talking about potential energy diagrams, the idea about what has to happen in order for a reaction to actually occur, and how we can sketch that out with this potential energy diagram, which is a review from Regents. You have already seen that. So, collision model, or the reaction model, is based on this fundamental idea, which should feel pretty understandable to you, that molecules must collide in order to react. That's the only way you're going to get an actual reaction occurring, the molecules actually hitting one another. And there are three factors that influence that collision and essentially determine if that collision will result in an effective reaction. And they are the activation energy, or EA, of the reaction, the temperature at which the reaction is occurring, and molecular orientations. And we're going to talk about all three of those. So first up is activation energy, or EA, and you have seen this definition in Regents. This is the minimum amount of energy that must be overcome in order to get a reaction to occur. It's the kickoff energy. All reactions require some input of energy from the outside. This is not saying that all reactions are endothermic, because what can happen is that although you need to input some energy, the reaction might then lose a greater amount of energy, so it then might release a larger amount of energy, which would result in an exothermic reaction. But regardless of whether or not your reaction is endo or exothermic, you always have to put some energy in to kickstart the reaction to really get it going. And that's the activation energy. And potential energy diagrams illustrate this activation energy. So these hopefully look familiar to you from Regents. We have obviously our reactants and our products. And reactants are always drawn on the left-hand side of the potential energy diagram, and products are always drawn on the right. So products are here. But activation energy, right, that is the energy between where the reactants are and then the top of this hill, right? That's the amount of energy that's needed to start the reaction. And over here we have where the reactants are and then the top of the hill. The important thing to note down here is that the overall energy change of the reaction, which is the difference between your reactants and your products, right? And again, overall difference between your reactants and your products, does not at all care about the activation energy. That's only what is the energy change between where the reactants are and where the products are. Activation energy has no effect on overall delta H or delta E. It's sort of referred to both ways. But activation energy absolutely affects the rate of the reaction. So in this reaction right here, its EA is smaller than this reaction over here, right? This has a much smaller activation energy. So this is the faster reaction because it requires less energy to come in from the outside in order to get going. It's not a faster reaction because it's exothermic. That is not why it's faster. It's a faster reaction because it has a smaller activation energy, right? Less energy needs to come in. And this is a slower reaction. Again, it's not slower because it's endothermic. That is not at all why. That is not the explanation. It's a slower reaction because it has a larger activation energy. More energy is required to start that particular reaction. So the idea is that if we have a larger activation energy as represented on a potential energy diagram, then we have a slower reaction. Catalysts alter potential energy diagrams because by definition one of the things that catalysts do is lower the activation energy of the reaction. They provide a different pathway, right? A catalyzed and uncatalyzed pathway, and we use that term. It's sort of like a different way to get from reactants to products, and the catalyzed path to get from reactants to products involves going over a smaller hill. So we've lowered the activation energy. So a lower activation energy will mean a faster reaction. Right? If the catalyst has ensured that less energy is required to kickstart the reaction, our rate is going to go up. The rate will increase. For reactants to form products, there are two main things that have to happen. First of all, the collision that occurs between the reactants has to have enough energy to overcome the activation energy. So it is entirely possible for two molecules to collide but not have enough energy to overcome that activation energy. If they don't have enough energy to beat the activation energy, we won't get a reaction from this. And what is it that influences whether or not the collision has enough energy to overcome the activation energy? The temperature of the reaction, because that is going to change the average kinetic energy of the molecules. The greater the average kinetic energy, the more likely it is that your collision will be able to overcome activation energy. But that's not it. That's not the only thing that influences whether or not a reactant will become a product. It also very much depends on the orientation of the reactants. The reactants have to be facing the right way. Molecules have sides. We call that polar, right? Molecules are polar. Certainly not all molecules, but many molecules are. And many times it's only one side of the molecule that's actually doing the reacting and the other side is not. So you have to make sure that when they hit the right way. They hit facing the right way, because if they don't hit facing the right way, then you're not going to get a reaction. So looking at this idea with potential energy diagrams and orientation, we have this reaction where we're starting with 2BrNO, that's our reactant. We're ending with 2NO plus Br2, that's our product. And over here, it's simply shown with a sort of a ball and stick model. Now the top, where our activation energy is going, we have something called a transition state. This is not an intermediate. An intermediate is something that's formed and then produced, but it's actually a lot more stable than this thing called transition state. Transition state is the species that you get at the height of the peak that's usually incredibly unstable, that will then immediately break down. And it's literally the transition between a step. It's sort of this midway point in one reaction mechanism step. So it's not the end of a mechanism step, it's actually the middle point. And we notice that for this reaction, what I want you to notice is that in the transition state, we started with 2BrNO, but the transition state involves this right here, that the BRs have essentially started connecting to one another. So we've wound up with the separate bromine atoms here, but now in the transition state, the bromine atoms have sort of started to come together, because if you'll notice in the products, the bromines are now totally bonded. So that means that in order for this reaction to occur, we have to have a certain orientation. This is the exact same reaction. So this is the 2BrNO over here. So this is referring to the same reaction from the previous slide. Now we have three possibilities shown here about how they can collide. In the first possibility, in the first way that they can collide, we notice that, okay, they're colliding almost vertically. But what's nice here is that the bromines are facing one another. So if they collide in this particular orientation, then yes, we get a reaction because the bromines came into contact in that collision. And then we have the second possibility about how they could collide. Well, now maybe they're colliding horizontally, but again, notice that the bromines are facing one another when this collision happens. So that's a good thing. That's what this reaction needs. So we will get a reaction. And in this final example, there are lots more ways that they could collide. This is just 3 examples that it's showing you. Notice that when they collide, right here, the bromines are not facing one another. And we don't get a reaction because that's not what's needed. So there's no reaction that occurs here. So they have to collide with enough energy, but they also have to collide with the correct orientation in order for a reaction to occur. Now, a little bit more on potential energy diagrams. What if I showed you a potential energy diagram that looked like this? What would you make of that? Because I know you haven't seen this one in Reagents. But this is a potential energy diagram that represents a 2-step mechanism. You've been seeing potential energy diagrams that represent 1-step reactions that occur in a single step. This is now a potential energy diagram for a 2-step reaction mechanism. Multi-step reactions have multi-step potential energy diagrams. That should somewhat make sense, right? If your reaction is taking place in more than one step, you essentially expect to see multiple activation energies, an activation energy for each and every step in the reaction mechanism. And so interpreting this, sort of looking at the different parts of, looking at the different parts of this reaction mechanism. We have, again, notice our reactants are on the left and our products on the right. That hasn't changed, but this bit right here, the sort of the first hump in the potential energy diagram, this is going to be step 1 in the reaction mechanism, and then this bit here, this is step 2. 2 steps. And then we have different portions of it. So this arrow shown right here, this is activation energy for the first step. So I'm going to say EA1, and then this arrow right here, and again, notice from where this dip is, from this low point again to the high point, so sort of again from where we start to the high point, from where we start to the high point, this is activation energy 2 for the reaction. And we can have the overall delta H or delta E of the reaction. That's still just the difference between the reactants and the products. So that's for the overall reaction. But then we can also ask the question, which step is the slow step? Is it step 1 or is it step 2? And then it's simply comparing the activation energies of step 1 versus step 2. So step 1 has a larger activation energy. So step 1 is slower. So if step 1 is slower, then think back to reaction mechanisms. That means that step 1 is the rate determining step. That means that the rate law for step 1 is the same as the rate law for the overall reaction. And we can also say that the overall activation energy is actually just going to be EA1, because overall that's the amount of energy that you have to input to get the reaction going. From that point forward, the amount of energy that's going to be released will be enough to compensate for the second activation energy. If you look at how much energy you get back after from here to here, that is more than enough to get you then from here to here for the second activation energy. So just to close, I have a reaction mechanism here, and we're going to draw a potential energy diagram, a quick sketch for this reaction. And I will tell you that this reaction is endothermic. So this is our overall reaction, the decomposition of N2O5, and the reaction mechanism has it occurring in 3 steps. So 3 steps is going to mean that we're going to have 3 sort of bumps on our potential energy diagram. The fact that it's endothermic means that we want to end with our products having a higher energy than our reactants, so we want to be aware of that. And then it says that step 1 is fast, step 2 is slow, and step 3 is fast. So this is going to mean that step 2, being the slow step, this is going to have the largest activation energy out of all 3 steps. So sketching that, we'd have a reaction progress on the x-axis, and then energy. Potential energy on the y-axis. So I already know that I want it to be an endothermic reaction. So wherever I start, I want to end higher than that. To indicate the fact that it's an endothermic process. Then I'll do step 1, kind of a small activation energy. Then I'm going to do step 2, a very, very large activation energy. And then I'm going to do step 3, smaller, and then sort of end there. So this shows that it happens in 3 steps. So this is step 1, step 2, and then step 3. And I'm showing that step 2 is the slow step by indicating that it has the absolute largest activation energy out of the 3 possibilities. So tomorrow you'll be answering some questions about reaction model and collision theory, and also on potential energy diagrams.